similarity statements. There's going to be a lot of those in this section. Similarity statement is a lot like our congruent statement. And the most important thing is that your letters are in the right order. Okay? That's the important part. So remember that as you go through this section, that when you're asked to write this similarity statement, that you put it in the right order. So we're going to start out with a postulate. And this first postulate is called AA similarity. What do you think AA means? Angle, right? So basically, this is kind of what we've already talked about with the other one. If, and notice it only has to be two. If two angles in one triangle are congruent to two angles in another triangle, the triangles are similar for sure. Now, why do we say that there's only has to be two of them? Yeah, because if the first two add up to a certain number and they're congruent to the same two in another one, then the third ones have to be the same thing too. Okay? So they just call this AA similarity. And so they're going to ask you to use this once in a while to prove that it is, or this can happen. The most important part of this is that you understand that your triangles, you want to look at them in the same orientation. So sometimes they'll try to rotate them, sometimes they'll try to flip them around. Just make sure that you look at it in the same way. So you might have to move your book or turn your book around. Okay? And then again, make sure that you write them in order. The letters, I mean. So then we go to our next theorem. And we're only at 7.2, and this is SSS. So this is a lot like our congruence. What was SSS? Side, side, side. So we're going to still use the sides, but instead of saying that they're congruent, all the sides have to be what? Proportional, right? Proportional. So if the measures, and again, if you don't want to write the words down, of corresponding, that's the important word in this one, right? Sides, and we have to make sure that it's all three sides. So you will have to check all three sets. Don't just do one, don't just do two. Of two triangles are, as Shayla says, proportional. The triangles are similar. So we're going to try to find that scale factor, right? That's essentially what we're doing. So we did a lot of this yesterday. We're just now giving it a kind of a theorem to prove it. And then finally, 7.3 is SAS. So what do we got?
Side angle side.
Side angle side again. But now with respect to this, we'd have to say what?
Similarity.
Okay, so S and S would mean if two sides of one triangle are proportional, with the included angle just means the angle that's in between the two sides that we're talking about, right? With the included angle being congruent in one triangle to a second triangle, the triangles are similar. I probably didn't write that the right way.
Sounds familiar.
But again, if you want the actual words. So basically, what's this saying? This is saying this. Again, if you don't like words, you like diagrams. Okay. Again, maybe they just show you a number here, so they would say, hey, this is what, 80 degrees, and this is 80 degrees. And then they would say, hey, this is 12, and this is 6, and this is 10, and this is 5. Okay? So we're proving that 12 to 6
It's the same as 10 to 5.
and 10 to 5 are proportional to each other, and then that angle in between them are congruent. Then we come back and say A, B, C, D, E, F. Then we could say this triangle right here, A, and again, it doesn't matter where you start with, right? I start with A, B, C. It's similar to, if I start with A, then I have to go to D, E, F. And this is what I'm saying, if it's tilted or upside down or backwards or something like that, then you just gotta make sure that your letters match up.
But the only way this works is if those two angles are congruent.
Right. If they're not congruent, then
This
you don't get side angle side. Yeah. Okay? So you could have other angles in there,
Yeah.
but it might not be the angle that I actually need. And then there is one more. I had 2 73s.
Yeah, I went 272, so,
I had 2 72s.
yeah, so 72 is Alright.
So I'm guessing this is 3 and this is 4.
Yeah.
Okay, sorry. Oh, I wrote it right up here, huh? 7-4, I don't know if you really need to write it again, but similarity of triangles is those words that we talked about for a lot of other things, right? Are reflexive, transitive, and symmetric. What does this mean again? What does, if it's reflexive, what's that mean?
Oh, it's not.
Say it one more time.
You can go over the-
Okay, that's one way of thinking of it. Reflexive in this part would probably mean something like this.
It's on the same thing, like on the same line. almost.
Everybody see that triangle? And if I draw just that simple line right there, does everybody understand that there's 2 triangles there?
That line.
Right? So if I call this A, B, and C, and then D and E are right here, does everybody realize that B is in both triangles? So B is reflexive to itself.
But,
That's the reflexive part of this.
no.
That what?
Because when they were D.
DB would be, but it would be a portion of AB for the big one.
I was saying D and E, wouldn't they both get triangles?
This one right here has nothing to do with the big triangle though. I mean, it's,
Inside.
yeah, it's just inside.
Uh,
Okay. So that's what they're really talking about with reflexive in this case, is that something's in both things. Symmetric, again, remember, is if I'm doing a proof and they wrote it backwards, and then you wanted to flip the sides, that's what symmetric was. And then the transitive property, remember, was what?
A equals B and B equals C and A equals C.
We pull out the middle and we have A equals C. Okay? So we've done all those a lot, you know, but they work with similarity things too. And then again, make sure that you answer the question, all right, for what is being asked. Okay? And a couple of the figures that we'll look at just here in a little bit, they do get a little confusing, so make sure you go slow and make sure that it works. So, if we look at this one right here, determine whether the triangles are similar, and if so, write a similarity statement. This is what we're talking about, right? So, if you look at this real quick, would you say that these 2 triangles are similar to each other?
Yes.
If you looked at it real quick, you might say no right off the bat because the numbers don't match up, right? But if I can find that third angle in both of them, right? And so does 58 fit into the right-hand triangle, and does 80 fit into the left-hand triangle?
Yes.
Yes. So are they truly similar? Yes. And so now you have to say your similarity statement. So again, you get to pick the first one, it doesn't matter. So somebody say one of the triangles in a specific order.
BAC, yeah.
BAC. So if we do BAC, then we have to match up the numbers in the right order, right? So if we say BAC, then the second one has to be what?
DEF.
DFE.
No, DEF, because we want BAC,
Oh, you want BAC. Okay, perfect. So, everybody see what we're saying there? Make sure your numbers match up. All right? And again, what's my symbol for similarity?
Basically, that's
Top of the congruence got a sign, right? The little squiggly. So here's another one. This one's kind of a little bit more interesting. So obviously here, the big thing here is that they show you that your QP and MN are parallel to each other. As soon as things show you that there's parallel lines, you should automatically think back to what?
all those.
Alternate interior angles, okay? So again, then that means this line right here, or this segment right here, are acting as transversals. Okay, so realistically, remember, when you're dealing with this alternate interior angles, it should touch the parallel side and it should touch the transversals. So those two angles right there are congruent, right? And then I could do the other set of alternate interior angles, or I could do these two angles right here, whoops, because those two angles would be considered what? Vertical angles, right? Vertical angles. And what is true about vertical angles? They're congruent, okay? Well, X is in both, but it's not truly shared in both, like this one. Okay? They're the exact same measurement
That's just
because
saying,
they're
that's
across.
just saying X is the point.
X is the point.
That's what
Yes. Okay, so do I still have AA? Yes, right? Because I can prove it right there, but I could have also proved the third one by the other set of alternate interior angles. So now, here's the key to this one. Make sure that you understand what angles go with what angles. Okay, so think about this one right here. Now, one triangle, I don't care which triangle, give me 3 letters in whatever order you want.
PQX.
PQX. Okay, so if we do PQX, then we have to do what? MNX. Okay? So this one kind of gets turned around, or flipped, kind of. Alright? Make sense? Those two are pretty much the same. These get a little interesting, I guess. So, here's one that sometimes they try to trap you a little bit. So, if we're looking at similar triangles, am I going to basically take that bow tie and flip it over? Or did I take it and maybe twist that one too? Okay, so even if you would check the 6 to the 4, see what I'm saying? So I'm basically flipping it over this way, the small one onto the big one. And so 4 and 6 would be in the same way. If you would go through and you would prove that that ratio didn't work for all the parts, then you should really check the other way, meaning maybe they took that little triangle and as they were flipping it, they rotated it too. So then like the DC could have actually been where CB was. So they could do that every once in a while. Now this one, I don't think it works that way. I think it's just like taking that small one and flipping it on top. But now you got to check all of them. Okay, so again, does it matter which way I do it? Meaning, does it matter if I do 6 to 4 or 4 to 6? No. Remember, I can do it either way because there's always 2 scale factors. So 6 to 4 is easy, right? 6 to 4 reduces to what? 3 halves, right? 9 to 6, 3 halves, right? Or 2/3. So I get 0.6666. So the last one might be a little hard for us to see because it deals with the decimal. So that's where I would just punch that one into my calculator. It's 5 divided by 7.5, 0.666666 also. And yes, it works. So are those two triangles similar to each other? Yes, by side, side, side. And then what is my similarity statement?
ABC is similar to DEC.
ABC is equal to DEC. And again, if somebody else started with C and did CAB, CAB, that's fine. But then we have to do CDE. Okay, so you just got to make sure that they're in the right order.
I know, that's
Okay? All right, questions there? But you got to do all three sets. So don't just say, well, I can see that 6 to 4, 9 to 6 work, and then I stop. You got to check that third side too, because they'll catch you on that. Make sense?
Yeah.
So then we have the one that we just talked about up here, and where this one catches people is that they don't do what? Add the two sides for the big triangle. So when I'm comparing the left-hand side to the left-hand side, remember the left-hand side of the big triangle is 15. I got to take 10 plus, or sorry, it's 25. It's 10 plus 15. So is 10 over 25 the same thing as 12 over 30? What's 10 divided by 5?
2.
What's 15 divided by 5?
3.
2/3, right? On the right-hand side, what's 12 divided by 6?
2.
What's 18 divided by 6?
3.
Does it work?
Yes.
Yes. So now,
So wait, you took the,
I did it, I split it into the little sections. You can honestly do the little sections if you know that the middle section is parallel. So you really should have done 10 to 25
so 10
and
divided by
12 to
25.
30. So this is right here.
The top number divided by the whole thing. Basically.
Yes,
kind
the
of-
top divided by the whole thing is this. The top divided by the whole thing is this. Okay? So do they work? Yeah, they're both 2/5. So again, everybody think, what is my similarity statement? Got it? What do you got? MNP is congruent to MRS. Similar, you're right, not congruent. And again, my M is in both of those triangles. Okay? I like that problem. That's a good one. Oh, I like this problem too. Not that one. So here's, not this one either. So this is basically just showing you that you can use the concept in the same way, but doing an algebra problem with it, okay? So basically they're saying, if we can prove that x plus 3 over 2x plus 10 is a true scale factor, then we would have, and it's the same as 4 over 10, then we would have side angle side again, right? Because of our alternate interior angles, okay?
So then you just solve it.
So basically, you're going to set up a proportion, right?
So x plus 3 over 2x plus 10 is equal to 4 over 10.
Right. And I'm going to set up that proportion, okay? And then I just solve my proportion. But again, same segments from the same triangle should either go on top of each other or across from each other. The spots are really important. You need to see the math. But this is the one where I'm saying, just because you find X, make sure you read the question and answer what they asked. I think they asked for the actual segments, so you got to put them back into RQ and TQ. Okay? Make sense? All right. Last one, right here. This is a good problem. So, with the ISAS coming up, this is something that might show up on those kind of tests. All right? There will be a lot of story problems, I know, because people just don't like story problems. Right? So, obviously, they're going to test this a little bit. So it says, Josh wanted to measure the height of the Sears Tower. Well, obviously, you probably can't just go and measure the Sears Tower, right? Unless you're going to jump off the top of the building with a tape measure and hold on for a while, right? So we're going to use the concept that we're doing right now, right? He used a 12-foot light pole and measured its shadow at 1 p.m. Why can he do this? he's knowing that that light pole is forming a right angle, right? And so if you have this pole, they recommend drawing a picture. So here's my Sears tower, and here's my 12-foot pole, okay? And then we're going to do the shadow of those, because we would know that the angle of the sun would be the same thing. Okay, so we're going to get a shadow, and the 12-foot pole made a 2-foot shadow. Well, we still don't know how tall the Sears Tower is, because that's what we're trying to figure out. But we know, or we could have measured the distance of that shadow, because that would have been something that we could have actually used a tape measure and walked it off if we wanted to. So we're going to just set up the same kind of proportion, right? And if you do this, obviously we're going to set up this proportion right there, okay? So, if you do this math, after we do our proportion, we figure out the height of the Sears Tower. So, it's kind of weird, but it essentially works every single time. How much? So, if you would actually jump off the Sears Tower with that tape measure and hold it along the side as you float it down, you should hopefully find out that it's 1,452 feet. Pretty cool, right? So instead of skydiving off the Sears Tower, you can actually use math. I know, weird, right? What? Yeah, Gabriel, you want to do a experiment?
Want to take one for the GPA?
Any questions there? So the next one, they do a light bulb, but it's basically the same thing, or a light bulb. Okay? Questions here? So you could actually use math to figure some of that stuff out. As skydiving off the Sears Tower? Probably not. All right, so here's your assignment, and then obviously your, like I said, there's a quiz tomorrow.